All right, welcome everyone to my 10.1 bonus video. In this video, we have a little bit of a roller coaster ride for a problem here. Again, chapter 10 is largely about parametric, and also a special situation of parametric would be polar equations, right? So here we have some parametric equations, a couple parametric curves here, or curves given to us in the form of parametric equations. And we're asked a true and false question, right? And so this would be maybe more on the conceptual side, typically, and we're just asked, right, do they have the same graph? And looking at this, well, they look like they are very different equations. And so at first glance, right, I think most folks would lean towards false, right? That this would probably be false. And then you could kind of start getting paranoid a little bit, right? And you say, well, is there something I'm not thinking about here, right? And then, well, we learned in 10.1 how to kind of transform back and forth between parametric equations and Cartesian equations. And Cartesian equations are nice because, I mean, we're graphing these things in the XY plane, presumably, right? You just have X's and Y's, so you can kind of look at them a lot, a lot easier and see. And so, okay, with this here, let's go ahead and check. I'm going to take these and maybe just starting with C1, I'm going to try to put this into its Cartesian form. So maybe for the first one here, I'm going to just write this as X. I know it depends on T, right? I'm going to write X is equal to T to the sixth power. And I'm going to go ahead and solve this for T. So if I solve this for T, I'm going to get T is equal to the sixth root of X. Okay, not very pretty, but fine, I can do it. Now let's go ahead and take this, and I'm going to plug this into my y equation. Remember, my y equation says y is equal to t to the fourth. And so if I go ahead and I plug that in, I'm going to get y is equal to, and then a t is the sixth root of x raised to the fourth power. And so if we'd like to, we can maybe simplify this just a little bit here. And I know, right, that this is really the same thing as x raised to the 1/6 power raised to the fourth power, right? The sixth root, just like the square root is the same thing as the 1/2 power, or the cube root is the same thing as the 1/3 power, right? The sixth root is going to be the same thing as the 1/6 power. Now, when I have powers raised to more powers, they multiply. And so this is going to be x to the 4/6, or we can simplify and just write that this is going to be x to the 2/3. So again, the Cartesian form of this is going to be y equals x to the 2/3 power. And so why don't we go ahead and check and see if we have the same Cartesian equation for C2. So I recommend maybe that you pause the video here, try this one on your own, then come back when you're ready to see the result. Okay, let's go over this one together. Similar to last time, I'm going to start off with x is equal to e to the negative 3t, and I'm going to try to solve this for t. So maybe I go ahead and I take the natural log on both sides, and then I divide by this -3. So we get something like this. I'm going to go ahead and take that and plug it into my y equation here. So again, y is equal to e to the -2, and everywhere I see a t, I'm going to put this. So negative the natural log of x divided by 3. Yep, there we go. And so now I'm going to try to simplify this, very similar to last time. So let's go ahead, right? We have two negatives. That's not so bad. And let me write this here. This is going to be e to the 2/3 of the natural log of x. And I remember, right, e's and natural logs are inverses of one another. If we had them kind of back to back here, then they would just cancel out and we'd be left with whatever's on the inside. Now, unfortunately, though, right, we have this 2/3 kind of blocking us there. So I think, well, if I could somehow get rid of that 2/3 there as my coefficient in front of the natural log, then I can use this great property. Again, it goes like e to the natural log of u is just equal to u. So, right, this is the inverse property that e and natural log share. And so to that end, I think about, right, there's a way, thinking back to our chapter 6, right, to move that 2/3. This was called the power rule for logarithms. Let's go ahead and write it up here. The natural log of a to the p is equal to p times the natural log of a. And remember, when this first came up, well, I mean, when this first came up in your algebra class, I don't remember what you were using it for, but I mean, primarily, we always went like this in this class, right? Oh, sorry. Forgot what I'm doing here, right? We always took the power up there and we typically brought it down, right? This was quite convenient when we were doing things like logarithmic differentiation. Now here's a case where we want to go in this other direction, right? So I'm going to go ahead and take the 2/3 that's in front of the natural log here, and I'm going to bring it up as the power. So this is going to be y is equal to e to the natural log of x to the 2/3 power. Now my e's and natural logs perfectly cancel out, and what I'm left with is x to the 2/3 power, right? Whatever's on the inside there, right? Whatever that u is, right? Whatever's inside of that natural log, that's what it simplifies down to. And so we can actually see that these things do have the same Cartesian equations. And so it's at this point, right, that we start to say, well, maybe it's true that these things do actually have the same graphs. But the last thing we need to do in order to figure out if these truly have, right, the same graphs is that we need to check and make sure, right? I know that these curves are going to lie on these Cartesian equations here, but I'm not sure if they get necessarily the entire Cartesian equation or maybe just a piece of it or something like that, right? And so we have to think about a little bit the range of these things. And so, for instance, let's just think about C1 for a second. If I plug in values of t, right? Again, t is ranging from -infinity to infinity when you're not specified a range. So if I plug in very, very small values for t, -100, stuff like that, all the way up to very, very large values, notice that both of these situations, right, we have raised to even powers. Whenever you have raised to even powers, that means that you're outputting, well, the smallest thing that you can output is 0, going all the way up to positive numbers, right? Positive infinity sort of deal. And so, for instance, for x, in my first case, so I'm just going to say, for C1, I know that x ranges between 0 to infinity. So no matter what I'm plugging in for t, very small things, very big things, right? Because we're raising it to an even power, it's going to become positive, or worst case, right? If I plug in 0, we'll get 0. Likewise, for y, you're going to get 0 to infinity as well. Because again, if you plug in t equals 0, you do get out 0. Otherwise, because it's raised to an even power, it's going to be a positive number. Okay, now we need to think about our second curve, right? Do we get all of those same values? Do we get all the way from 0 to infinity, right? If we only got, for instance, from 5 to infinity, well, then they would lie on the same curve, but they wouldn't have the exact same graph, right? Because C2 wouldn't have as much as C1 does. And so the question is, do we also get 0 to infinity? Or right, maybe in C2, we get -infinity to infinity, right? Maybe the x values, right, there's more to this curve. And you actually get more than C1 has. So that's the last thing that we need to check here. And so, okay, thinking about e to the -3t. Well, I need to remember what e looks like. Maybe I'll pull off to the side here. E looks like typically, right, if I just have e to the x, it looks something like this. Now, this -3, though, is going to be doing a little bit of stretching, right? And it also flips it in this horizontal direction. So in fact, this is going to look something like this. So notice the outputs here. Again, I'm thinking about my inputs are t's and my outputs are x's right now. So as I put in a whole variety of t's, again, t can range from -infinity to infinity here. Notice that I'm going to get out positive values. But that's the thing, strictly positive values. That is, x is going to range from 0 to infinity, but not including 0. there's nothing that I can plug in for t where this thing right here is actually going to output 0. And so at this point, I now know for sure that the answer is going to be false. But like I said, it's a little bit of a roller coaster ride, right? Kind of your intuition at first was like, these look different. But then you found out they're actually the same Cartesian curve. But sadly, they don't get all of the same points. The y value will also have the same issue, right? If I think about the graph of this, so t and y, this one's not going to be stretched maybe as much. I don't know, I'll do something like that. But again, kind of as you plug in larger and larger values of t, it does have an asymptote towards 0. You get very, very close to 0, but you never achieve 0, right? And this other curve, right, can achieve 0, right? If you plug in t equals 0, you can actually get the point 0, 0. So C2 is actually going to be what we call a subset of C1. C1, they contain a lot of the same points, right? But just C2 doesn't have the point 0, 0. So no, they do not have the same graphs. They're off, but sadly, they just miss 1 point. So the main takeaways I want you to get from this, right, is that first of all, kind of this conceptual idea that there are many different parameterizations for any Cartesian equation. And they can look very different, right? I mean, these things look quite different from one another. And, right, in order to check if two parameterized curves, right, two equations that you're given, have actually the same graph, what we need to do is, first of all, convert to Cartesian, right? If they don't have the same Cartesian equation, then you're kind of out of luck, right? They don't have the same graph then. Unless we're doing, I guess the caveat there would be if you have some like trig functions, right? Many times trig functions, they have different representations for actually the same curves. So for instance, right, if I said sine squared x versus 1 minus cosine squared x, right? That would be maybe an example where these actually do have the same graphs, even though they look a little bit different. And then the second thing is that you need to do a check of the ranges, right? Do they actually achieve the same points? And so in our case, right, we had, once we converted to Cartesian, they actually have the same Cartesian equations. And so they stand a good chance of having the same graph. And yet when we checked their ranges, we saw that, well, one could actually get the point 0, 0 while one couldn't, right? And so this was kind of an extreme case, right? They were only off by 1 point, but they could be off by more than that. Okay, the final thing that I want to do in order to finish up this video is that I would like to show you kind of what this is looking like in Desmos. And so let me go ahead and switch over here and get this ready for you in Desmos. All right, guys, here I have in Desmos, right, a few things graphed. Right now, I'm only showing, right, this Cartesian equation that we found, this y equals x to the 2/3 power. And we can actually see, right, it makes sense. You can plug in positive x's, you can plug in negative x's, all that good stuff, right? Of course, the y values always end up being positive, but this is what the curve looks like for y equals x to the 2/3 power. Now let's go ahead. I'm going to turn this off really quick, and I'm going to plug in just our parameterized curve, right? This x to the 6th and x to the 4th. And so when we do that, notice that I have it for about 10,000, right? From negative 10,000 to positive 10,000 or so. And you can see it's kind of this curve right here. Of course, it goes on quite a bit, but it's having a hard time maybe doing all this computation. Let's just maybe make this a little bit smaller here. Because these are being raised to such big powers, we don't really need a whole lot. Let's just do from negative 10 to 10. There we go. You can see that that kind of goes on for a while. So of course, this maps onto, right, this y equals x to the 2/3 power, right? So this parameterized curve does overlap with this Cartesian curve. Notice that you don't get the entire thing though, right? You get only from 0 and beyond, because again, right, when you raise things to the 6th power to the 4th power, right, these even powers, right, you're only going to get out positives for x's and positive for y's. And so in this case, right, you get a piece of this Cartesian curve. Now let's go ahead and take a look at, I'm going to turn all this off, and I'm going to do the e's, maybe the same thing as before here. Let's just kind of bring this down a little bit, just so that way it's not trying to do a lot of computations here. And again, you can kind of see we get the same sort of picture. Again, it overlaps with this Cartesian curve, this y equals x to the 2/3. But as we saw, right, it doesn't contain the point 0, 0. There's nothing that you can plug in here. You get very, very close to this, right? As I zoom in, right, you get very, very close to it. It seems like it gets close to 0, 0, and it does, right? But you can't ever achieve the point 0, 0. So, all right, this is kind of what we did, right? We did a bunch of algebraic maneuvers, and I just kind of wanted to show you what this all looks like when you consider the graphs. Thank you so much for watching. I hope you guys have a great weekend, and I'll see you out there.